Hello everyone, today I am going to discuss three chapters, that is system of particles and rotational motion, and in the properties of bulk matter where I am going to discuss the properties of solids as well as properties of fluids. So this is a three chapter series. This is the part 3 of the PU1 series. Obviously we want to complete this as soon as possible. Also, fair warning, the concept from these three chapters are little difficult, and if you have not studied them in your PU1, you can skip this lecture, okay? But obviously if you are in the pursuit of scoring as much as possible in your KCET exam, then definitely you cannot skip it. But if you have not touched these chapters at all in your PU1 preparation, then you can skip these chapters because the chapters concepts are little weird and little difficult for a beginner. So let's start with the session anyway. So first we will see what are all the important concepts. In system of particles we have center of mass, center of gravity, we have the concept of torque, angular momentum and momentum inertia. These are the main parts of this chapter. In the properties of solids chapter, we have modulus of elasticity. There are 2-3 different types of modulus of elasticity. Obviously Young's modulus is the most favorite one. Then we have Poisson's ratio, we have elastic potential, energy as well. Next we have in the properties of fluids, streamline flow, we have Bernoulli's principle, we have viscosity, and we have surface tension. So these are the important concepts from the chapter properties of fluids. Now if you want to practice questions which are aligned with KCET exam, also if you want to practice 60 questions in 60 minutes, exact paper like situation, exact exam like situation, definitely you have to go through our Abhyas test series, which is currently available at a price of 4098. You can go and check in the link given in the description, and you can download, you can fill the form, and then from there you can download the app, okay? Don't go anywhere without filling the form. Form fill up is essential. Also the price is 4098. You can purchase it at one time cost only, and you will get a lot of benefits. You will get tests every day. You will also get live doubt clearing session. Also you will get all the one shot videos. You will get 5 previous year questions inside. So everything you will get from this one place. So don't wait, just go in the link below and purchase it today. Now let's start with the first chapter, system of particles and rotational motion. So first we are going to discuss center of mass. The center of mass of distribution of mass in space is the unique imaginary point where we can consider the entire mass is located. Now this point can be inside the object, it can be outside the object as well. For example, if it is a solid object, for example we have a solid square plate, then the center of mass will be located exactly at the geometric center. If it is a circle, if it is a circular ring, obviously the center of mass is located at the center, okay? But this center here, there is no material. In this position there is no material, so the center of mass is basically outside the object. And there are very specific structure. For example, these positions are still geometric centers, but if you consider some specific structure like this, okay, and in that case the center of mass is located somewhere which is not only outside the object, it is also not in the geometric center of the object, right? So this is also possible. Now anyway, the center of mass of a system of particles moves as if all the mass of the system was concentrated at the center of mass and all the external forces were applied to that point. So basically, why do we use center of mass concept? Because in our physics most of the laws are basically applicable to point objects, right? But in reality there is nothing, no object is a point object except maybe electron, proton, those smaller objects, right? But other than that, all the objects that we see in our day-to-day life are basically bulk objects, right? So how can we apply the laws of physics? For example, laws of motion, Newton's laws of motion, they are all applicable to point objects, they are not applicable to bulk object. To do that, what we have to do, we have to consider the center of mass. If we consider the center of mass, then the center of mass, motion of the center of mass can be considered to be a point object, and all the forces acting on it, our laws of physics is still valid in all cases, right? That is why center of mass is very, very important. Let's see one question. Now this is related to angular motion, okay, angular speed, angular acceleration. Obviously, what is angular speed? Angular speed is theta by t, and angular acceleration is omega by, so angular speed is theta by t, which is similar to linear motion, okay, and angular acceleration is omega by t. Okay, so v by t was in case of this, so the same thing, but in case of rotational motion we use angular motion. And what is the relationship with linear motion? Okay, so v equals to r omega and a equals to r alpha. These are the relationship in between angular motion, angular velocity, angular acceleration. Okay, so you can remember this equation. Anyway, we will do this, we will learn about it through an problem. It is from 2021 KCET exam, and the angular speed of a motor wheel is increased from 1200 rpm to 3120 rpm in 16 seconds. The angular acceleration of the motor wheel is, so obviously initial speed was 1200 rpm and final speed is 3120 rpm. Now what we have to do, we have to convert rpm into radian per second. So omega is radian per second. So what is delta omega in this case? Delta omega is 3120 minus 1200, but this is in rpm unit. Unit you have to be careful about. Okay, so it will be 800, 920, so 1920 rpm. Okay, so this is the conversion in rpm. Now we have to convert it into radian per second. So remember what is rpm? Rpm means rotations per minute. Rotation per minute. Rotation means one complete rotation. So if it starts from here, okay, and if it completes one complete rotation, what is the angle? The angle it subtends in one complete rotation is basically 2 pi, right? 360 degrees. 360 degree means 2 pi radian. We have to convert it into radian. So rpm basically means 1920. rpm means 2 pi. And what is the time? It was in per minute, but our unit is in seconds. So rpm means 2 pi by 60. Okay, so whenever you want to convert from rpm to radian per second, you have to multiply with 2 pi by 60 factor. Now let's solve it. So it will be 3 6 are 18 and 2 6 are 12. So it will be 64 pi radian per second. So this is the delta omega, change in angular speed. Now what is the time? Time given is 16 seconds. So what is alpha? Alpha is delta omega by time. So 64 pi divided by 16, so it will be 4. So it is 4 pi radian per second square, similar to that of the unit of acceleration. In case of acceleration it was meter per second square. In case of rotational motion it is radian per second square. So correct answer is 4 pi radian per second square. So this is the correct answer, right? So this kind of question also comes, but if you don't know these basic formulas, you will not be able to solve it, even though the problem is very, very simple, easy to solve, right? Now let's move on. Let's see the moment of inertia. So analog of mass in rotational motion is called moment of inertia, and it is denoted by term I. Normally it is given by m is equal to m, I is equal to mr square. Okay, so for a point object from rotating around some axis of mass m, point object at a distance r, then this is the formula for moment of inertia. But they are for different object based on the geometry of the object and rotational axis of the object. Moment of inertia changes, we will see that. But what all it depends on? It depends on its shape, how it is looking like, what is the shape of the object, depends on the position of the axis of the rotation. Okay, so even if the shape is same, if you change the position of the rotation axis, the moment of inertia might change. It depends on its size, how big it is. It depends on its mass as well. Obviously it depends on the mass, right? So these are all the factors on which it depends. So now based on this, maybe there will be an MCQ question, which on the following factor moment of inertia does not depend. So you have to identify, okay, it depends on shape, depends on position, depends on the size, depends on the mass. What else can be there? And let's see. So these are the main 5 objects for which you have to remember the moment of inertia. Obviously this is the most important, ml to the power ml square by 12 for a single rod along the any axis. Okay, perpendicular to the rod and midpoint. So if it is a perpendicular to the rod and midpoint, then not along the axis of the rod, obviously, then the moment of inertia is ml square by 12. So this is the most important moment of inertia formula. You have to remember these formulas, at least these 5 These 5 are very important. The thin circular ring for radius is mr square. For if it is rotating along the diameter, then it is mr square by 2. Okay, now if it is a solid ring, if it is a solid disc, okay, and it is rotating along the center, then it is mr square by 2. And if it is along the diameter, it is mr square by 4. So there is a symmetry, right? mr square by 2, mr square by 2, mr square by 4. So if it is solid, it is mr square by 2. If it is along the diameter, mr square by 4. For simple ring, it is mr square, and for diameter always half. For diameter, along the diameter, it is always half of that of the along the axis. Okay, perpendicular to the axis of the disc. Right, so these are the 5 that you have to remember, easy to remember, not super difficult. Okay, other than that, there are all other different type of objects, but those are not important, at least for KCET exam. For any other competitive exam, those are important, but at least for KCET exam, these 5s are necessary. Now let's move on. Torque and angular momentum. Let's see. The rotational analog for force in linear motion is moment of force. It is also referred to as torque or couple. So moment of force, torque, couple, they are all same thing. Okay, so one person have different names. For example, you have one name at your home, one name at your college, one name called by your friends. So there are different names, right? So torque also has different names, like Sri Krishna. Okay, so moment of force, torque, couple, everything is same. So it is torque is equal to R cross F. Also torque is rotational analog of force, and in force we know that in normal linear motion F is equal to ma. So torque should be equals to I alpha, right? So where alpha is the angular motion, angular acceleration, I is the mass, angular moment of inertia, right? So I alpha is the formula for torque. Okay, generally most commonly we will use this formula, R cross F. In fact in electrostatics as well we have used this concept, right? Now the quantity angular momentum is the rotational analog of linear momentum. Okay, angular momentum is rotational to linear momentum. What does that mean? That means that L equals to R cross P. Okay, so in for force there was force, for momentum there is momentum, and it is also written as I omega. Obviously in normal momentum is basically given by mv, so angular momentum will be given by I omega. So everything corresponds to the equivalent of rotational motion. What else? The time rate of total angular momentum of a system of particles about a point is equal to the sum of external torques acting on the system and taken about the same point. So It is similar to that of second law of motion. You can call this as a second law of motion for rotational motion. What is the meaning of that? Very simple, that torque is basically dl dt. Okay, rate of change of angular momentum is equals to torque. Okay, so time rate of change of total angular momentum of a system of particles about a point, but the axis or the point about which is very important in rotational motion. You have to define a point about which you are measuring angular momentum, you are measuring torque. Okay, so about that same point it should be always same. So same as linear motion where F was dp by dt, right? Let's move on. Center of gravity. This is also very important. The center of gravity of a body is defined as the point where the total gravitational torque on the body is 0. So suppose we have an object, okay? Now there is some gravitational force acting on it. So if you consider about some point, okay, there will be some torque acting. There is an R, there is a gravitational force, so R cross F is not 0. But there will exist a point where if you consider all the torques acting on the body with respect to which, if you try to find all the torques and then add them. Okay, if you add all the torques acting on the body, tau 1 plus tau 2 plus tau 3, okay, then the total torque of on the system will be 0 about some point. Okay, so that fixed point is called center of gravity. It is not any arbitrary point. It depends on most cases for symmetric objects. Center of mass and center of gravity generally coincide, but this is not a necessary condition. Okay, center of gravity and center of mass may coincide in certain cases, but that is not always true. Okay, the center of gravity of the body coincides with the center of mass in uniform gravity for small objects. Okay, if the object is small and if the gravity is uniform, okay, so gravity is uniform, then we say that center of gravity and center of mass generally coincides, and if it is a symmetric object also. Okay, basically the two are different concepts. The center of mass has nothing to do with gravity. So by what I want to say, that center of gravity comes from the concept of gravitation, which is a vector force, whereas center of mass comes from the scalar consideration, where we consider position and mass of individual objects. From there we get the center of mass concept, which has nothing to do with center of gravity, but because of the symmetry, some cases for small objects center of mass and center of gravity can coincide, but that is not always true. Now let's move on to the next part, properties of solids, the second chapter in our discussion. So let's start with properties of solids. First, stress and strain. Okay, stress is what? When a body is subjected to a deforming force, a restoring force of equal magnitude but opposite in direction to the applied force is developed in the body. The restoring force per unit area is known as stress. So stress means what? So when I am asking you to study, okay, your internal body, your internal brain is saying no, I don't want to study, I have to watch IPL match. So basically this internal restoring force, whatever is happening inside you, which is not allowing it to study, that is basically giving rise to stress. Now in the exam is coming every day, exam is nearing, and you are saying, oh, I have not studied, so I am in stress. So stress is basically same thing, okay, but it is in case of an object, not a human mind stress. It is for an object. If you try to compress it, if you try to change its dimension, maybe its length, its whatever it is, if you try to change its dimension, there will be some resistance within the object. Okay, that resistance force, according to Newton's third law, up to certain limit it will try to prevent the whatever the force is applying on the object. Okay, and this restoring force per area, per unit area, so there is an area, okay, based on the area the restoring force will change. Now the restoring force per unit area is called stress. Okay, stress is fixed. Now strain is different. Strain is the change in its dimension is called strain when external force acts on it. There are three ways in which a solid may change its dimension. Okay, so you can change the dimension of an object in three different ways. Okay, stress is only one. Force restoring force per unit area. Basically in most cases applied force itself acts as the restoring force, okay, because within some limit restoring force and applied force are same. If you cross that limit it will not true, but within certain limit restoring force equals to applied force. Now what are the three types of dimension? First is longitudinal strain. Longitudinal strain means if you try to stretch it, if you try to stretch the object lengthwise, okay, if you try to stretch, so for example if you take a rubber band, if you stretch it, what happens is that it becomes thinner, right? The thick rubber band becomes thinner as you stretch it. So this is called longitudinal strain, okay, and it is basically delta change in length divided by original length. Next is tangential or shearing strain, which is very interesting. If you have a book, and if you try to apply some force along the surface of the book, okay, you have a book on your table, you apply some force on the book side of the table, it will even though you can extend it, but still it will try to prevent it from expanding, okay, that is called longitudinal or shearing strain. And last is hydraulic strain or bulk strain, which is basically if you apply some force under which its volume changes. For example, you take a balloon and if you put it under the water, it gets shrink, right? So it experiences forces from all the directions and its volume shrinks. That is called hydraulic strain or bulk strain, sometimes volume strain. So they are all same hydraulic strain. Okay, now as you can see that strain is a dimensionless quantity. Okay, delta L is unit of length, L is also unit of length, so unit of length divided by unit of length, so there is no unit, so this is a dimensionless or unitless quantity. Stress is not unitless, stress has same dimension or same unit as pressure, okay, pressure is also F by A, strain is also stress is also F by A, okay. Now Hooke's law. So for small deformations, the stress and strain are proportional to each other. So stress and strain are proportional to each other. So basically F by A is proportional to strain. Okay, now basically whenever there is a proportionality, there is a constant of proportionality. We will talk about that in a while. So this is the Hooke's graph. So this is called Hooke's limit. Up to this limit, this is called Hooke's limit. Up to this range, Hooke's law is valid, okay, and if you apply stress to an object, it slowly up to some point, then after this point it breaks, okay, this is the proportional limit. Okay, there are different explanation of this point, but I am not going to explain, but you should remember that below 1% Hooke's law is valid. So if the deformation of the object is small, that is below 1%, so if you stretch the object and its elongation is less than 1%, then the Hooke's law is valid. Okay. Now modulus of elasticities are the constant of proportionalities which comes from the Hooke's law. There are mainly two modulus of elasticity that we are going to discuss. First is Young's modulus. Longitudinal strain is directly proportional to longitudinal stress. The constant of proportionality is called Young's modulus. So Y is basically F by A divided by delta L by L. Very important, and it is also unit of pressure. So the unit of Young's modulus is Pascal. Okay, very important because the division was dimensionless. Next is hydraulic stress. It is also same thing. I think that the symbol is incorrect. It is denoted by K. The ratio of hydraulic stress to the volume strain is called bulk modulus. Okay, bulk modulus is our hydraulic modulus, whatever it is. Okay, so bulk modulus is delta V by V, and F by A is the F by A is the hydraulic stress, and delta B by B is the hydraulic strain or volume strain, and this is called bulk modulus. It is basically when you are compressing an object, right? Now let's move on. See one question. A thick metal wire of density rho and length L is hung from a rigid support. So this is object of length L, and density rho, density is rho. Okay, length L is hung from a rigid support. The increase in the length of the wire due to its own weight. So when you hung it like this, okay, because of its own weight, the object will expand. There will be some expansion. So we are trying to find this expansion of the weight of the this expansion of the object. Right now, where will be the force acting? Force will act at the center of mass, which is exactly at the center of the object. Okay, so if this is the length, then this will be L by 2. Okay, the force will act here. So what is the force? Force is mg, right? Now if you consider the cross section to be, cross section of the rod is A, then what is the volume? Volume is length into cross sectional area, L into A. So what is mass? Mass is L into A. Okay, so L into A into G is the force. So what is now if you consider Young's modulus, that is F divided by A into delta L by L. Okay, so this is the definition of Young's modulus. Now we have to calculate delta L. So delta L by L equals to F divided by A divided by Y. Now put the values, put the value of everything, of this force basically. So let's put L A G divided by A divided by Y. So we get A cancels, LG by Y. Now this is delta L by L. So what is delta L? Sorry, there is one more rho over here. Sorry. Why rho? Rho is to consider this is mass. This is volume, this is density. Volume into density is mass. So mass is rho V. Okay, so I missed that rho. So rho Lg is here. So delta L will be rho L square G by Y. Okay, rho L square. So this is the correct answer, rho G L square by Y. Obviously, even though it is acting on L by 2, there is nothing, not such effect, because we are not calculating any torque or anything. So this will be simply the formula. Next question. The ratio of lateral strain and longitudinal strain is called Poisson ratio. Okay, Poisson ratio is very interesting concept, and it is given by nu. Poisson ratio, the symbol is nu, same as frequency, and it is basically lateral strain, that is delta D by D divided by delta L by L. What is delta D by D means? Suppose you have a thick rod. Okay, you have a thick rod. Now you applied some force on it. Okay, you have some thick rod like this. You applied some force on it, and what happens is that it size gets changed as it is getting expanded, right? If you apply the force, okay, it becomes thinner, right? Now as it is getting thinner, so this is the diameter, say D. As it is getting thinner, its diameter will change. So what will be the suppose the shrink in the diameter, the shrink, original diameter was this, the shrink, the change in the diameter is delta D. Now original length was L, the increase in the length is delta L. Okay, so the ratio of delta D by D divided by delta L by L is called Poisson ratio. So when you stretch something, it becomes thinner, and that is because of Poisson ratio. Okay, and this can also be written as delta R by R in case of you are using radius. Okay, you don't need to convert it into diameter unnecessarily as long as it is same. Okay, so delta R by R if you are using radius, right? Now Poisson ratio can be negative for certain material. Okay, there are certain material exist in nature. If you expand it, instead of getting shrinked, it can expand as well. Okay, the maximum value of Poisson ratio is 0.5. It cannot be more than 0.5. 0.5 is the maximum value. Now when this is happening, this happens when the volume is unchanged. So that means if you expand it, okay, you are expanding the material, but if its volume remains unchanged, that means whatever is the initial volume and the final volume, if they remain unchanged, that in that particular case the value of Poisson ratio is 0.5. Now you might face a question, objective question, 1 mark question based on this concept. So that is why this is very, very important. Now, elastic potential energy. So what is the formula for elastic potential energy? Elastic potential energy per unit volume or elastic potential energy density is basically half stress into strain. Derivation obviously is not required. What is total potential energy? Total potential energy is potential energy density into volume. Okay, this is the total potential energy. So if you stretch something or if you compress something, definitely some energy is getting stored. So that is called elastic potential energy. It is basically stress into strain. Now next is properties of fluids. Let's see. First we are going to discuss about pressure. Just to refresh, Pascal's law, you have learned it in I think 7th or 8th grade. Whenever an external pressure is applied to on any part of a fluid contained in a vessel, it's transmitted undiminished and equally in all directions. So if you have an object, suppose you have a rubber ball, you made some holes into it, and then you fill water inside it, and if you press the rubber ball with applying pressure, then the water jets that will come out through those holes will be equal in all direction. That is basically Pascal's law, right? So force getting transmitted equally in all direction, pressure getting transmitted equally in all direction. Applications, hydraulics, we apply this in hydraulics. Next part is gauge pressure. What is the meaning of gauge pressure? Gauge pressure is rho gh. Suppose you have a liquid, okay, you have some liquid and you want to find pressure inside that liquid. Okay, the density of the liquid is rho, gravitational acceleration at that location is g, and if the depth is h, then this term rho gh is called gauge pressure, or pressure only due to this liquid column. Pressure only due to the liquid. Why? Because there is something called total pressure. To find total pressure, you also have to consider the atmospheric pressure. Okay, so this is only gauge pressure, which is only due to the liquid column. But if you add atmospheric pressure to this, then you get total pressure at that point. Okay, you get total pressure at that point. Clear? Now let's move on. Streamline flow. If you see this flow, this motion, this is completely muddy, and you cannot not muddy, milky, and you cannot see the flow of water clearly. Now if you see this one, you see that water in each and every water level, streamline. So basically this is a streamline motion where this is falling slowly and you can see it clearly, where here the water are falling like this, and this is basically called turbulent motion. The flow of fluid is said to be steady if any given point the velocity of each passing fluid particle remain constant in time. So the speed of this water molecule and this water molecule, they are same. Okay, each passing molecule coming out of this tap, they are passing with the same velocity, same speed. That is called streamline motion. The path taken by a fluid particle under a steady flow is called streamline. It is defined as the curve whose tangent at any point is in the direction of the fluid velocity at that point. So basically it is basically a curve. Okay, and if you draw the tangent at any point, you will get the direction of fluid velocity at that point. Okay, so this is the definition of streamline. Sometimes this is also called laminar flow. Okay, laminar flow is basically streamline flow, streamline motion. Okay, now another very important concept, Bernoulli's principle. Okay, so what is the Bernoulli's principle? Because before going into that, we have to know equation of continuity. So if suppose through a pipe A1 liquid is coming with velocity V1 and it is exiting through another outlet A2 having velocity V2, then equation of continuity says that whatever liquid which is coming in, that is A1 V1, should be equals to whatever liquid is going out. And this is not only restricted for only single pipe structure. It is, suppose we have a structure like this. So here we have, suppose water is coming through a surface say A1 and velocity is V1 and it is exiting through this one A2 V2, A3 V3, A4 V4 and A5 V5. Okay, in fact you can say, okay, there are water can go through another inlet, water can go through another inlet over here. Okay, so no matter what, so you have to consider that whatever coming in, okay, A1 V1, that should be equals to sum of whatever going out. It is similar to that of the junction rule of Kirchhoff's law. Remember junction rule of Kirchhoff's law, that whatever current is coming in and whatever current is going out, the sum should be same, right? So here we have only one inlet, but we have 5 outlet. So A1 V1 should be equals to A2 V2 plus A3 V3 plus A4 V4 plus A5 B5, right? So this is the main important part of this equation of continuity. So the fluid, whatever is going in, that should only can be divided into different parts. Okay, nothing else can add up or less. Now, next is Bernoulli's principle. So Bernoulli's principle says that now we have a liquid going through a pipe. It is basically mainly about liquid motion. So liquid is passing through this, and some liquid is kept at height h1, some liquid is kept at h2. So Bernoulli says that pressure plus rho v square, rho is the density of the liquid, into v square is the speed of the fluid, plus rho gh is obviously rho g and height from which it is kept, that for a given liquid passing through a pipe will always be constant. So P plus half rho v square plus rho gh is always constant. Now speed of efflux. Speed of efflux is very important concept. You have some container. Okay, you have some container and you fill that container with water. Okay, if you have filled that container with water, but you have covered the top part is fully covered. Okay, and you made a small hole at some end. Okay, so basically you have taken a full water bottle, a plastic Coke bottle, and then using a needle you put a hole into that water bottle. Then what will happen? The water will come out from that bottle, right? Now this is H is depth from the top of the liquid. Okay, so this is very important. It is not the height, it is from the top, so the depth. Okay, so then what will be the speed of this outcoming liquid? The speed of outcoming liquid is given by 2gh, here h is the depth, okay, plus 2 into P naught minus PA. Okay, PA is the atmospheric pressure and P naught is the pressure due to the liquid. So P naught, whatever the pressure here, P naught minus PA divided by rho. Now if you keep this part open, if you now remove the cap of the bottle, then atmospheric pressure and the atmospheric pressure from this side, they will be equal. So P naught and PA both will be equal. So P naught minus PA will become 0. So the speed of efflux will become V1 equals to square root of GH. This is the important formula. Once in the previous years this formula was asked, you have to remember 2GH is common plus 2 into P naught minus PA by rho. Okay, but this formula is must to remember from this part. Now let's see about viscosity. Viscosity is, we have, suppose here we have a river bed, okay, and the bottom we have, this is the bed of the river and this is the liquid. Now once the liquid is flowing through the river bed, okay, not all the layers are moving with same speed. The layer that is exactly after the river bed, that layer is not at all flowing. The layer above that is flowing with very minimal speed, and as you slowly going up, the upper layer is moving with the highest speed. So this is why this graph is shown like this. So this portion has moved very far, whereas this portion has not moved very far. So the displacement of the upper layer is given by delta x into is equal to V into delta t. Okay. Now this is happening because of the one layer of liquid is having a kind of friction amongst their layers. Okay, so viscosity is a liquid friction. We have seen friction when one object tries to slide over another in solid object, then there is friction force, but when liquid tries to slide over another liquid, there is a viscous force, and viscous force, viscosity is given by F by A divided by V by L. What is L over here? L is the height of the liquid from the ground. Okay, sometimes this is also called dV by dl. Okay, sometimes this is called as velocity gradient. This is called velocity gradient. Okay, dV by dl. So how velocity is changing as you are going up. Okay, so V by L. Now another important formula related to viscosity is that Stokes law. When a body falls through a fluid, now this is when the liquid is trying to flow. Now let us consider a liquid is static, but I am dropping one object into it, say a ball. Okay, iron nail or iron ball, okay, ball bearing. I am trying to drop it through a liquid. So it will not go down as it was going down in air, right? It will slow down. Why? Because the liquid is applying viscous force to the object which is falling through it. Okay, when a body falls through a fluid, it drags the layer of the fluid in contact with it. The drag force is given by F equals to 6 pi eta RV. Okay, 6 pi is a constant, eta is the viscosity. Eta is viscosity, r is the radius of that object, and v is the velocity of that object. Okay, generally after some time it attains a constant speed. That constant speed is called terminal speed. This v represents that terminal speed. Okay, generally v can change. This drag force will be there. If it is if the velocity is changing, drag force still will be there, but drag force will also change. But if the drag force is constant, that means this velocity has attained a constant value. Okay, so this v will be a constant, that is a terminal speed. So you will see some questions based on terminal speed. That means you have to use this formula with a constant v. That's it. Okay, don't think too much about the formula. Only thing you have to remember is that this is a force formula. There was a very difficult question came, I think 24 or 23 from electrostatic, where you have to apply this concept as well as concept of electric field, electric force, a lot of difficult concept. That was one of the most difficult question throughout the history of KCET. Okay, so that is why I said if you don't have any idea about these three chapters, you can skip it. But again, you are at a loss. Some questions from second PU might be based on these concepts, right? So even though the concept is not directly related to this chapter, that might be related to second PU chapter. Now let us discuss about surface tension. Surface tension is so for example, this bug is staying on the water as if the water is like a stretched membrane. Like, so this stretched membrane, why this bug is able to stay on this water? Because of the surface tension. Okay, it has some small thing which is creating a surface tension on the liquid, and based on that it is basically just like a stretched membrane for this bug. Okay, and the surface tension is basically F divided by 2L. Okay, and capillary rise, another important formula is given by 2s cos theta rho g r. What is the capillary rise? Capillary rise means if you take a pipe and if you put it inside a fluid, if you take a small pipe and if you put it inside a fluid, okay, the fluid will automatically start to rise inside that pipe. This is called capillary rise. You can increase the capillary rise by creating vacuum over here. That's how we use straws to drink liquid. But even if you are not sipping from the straw, the liquid will still rise inside that pipe, and that rise is called capillary rise. Okay, and this depends on this contact angle theta. Okay, and the height is basically given by 2s cos theta by rho g r. It depends on the radius of the pipe, it depends on the density of the liquid, it depends on gravitational acceleration at that point, obviously. Now there is a very interesting question, okay, just for your knowledge, that suppose this capillary rises to a height h. Now if you cut it, say at a height h by 2, then what will happen? Will we be getting a fountain effect? So what is the meaning of that? So liquid wants to rise to this height, but you have cut it before that, even before that. Then what should have happened? The liquid should go up and then should come back, like we should get a fountain effect. Will we observe that? No, this is not possible. Okay, because to that happen, when the liquid is rising up to this point, okay, the surface will be flat. Okay, surface will be flat, and because of this flatness, liquid will no longer able to rise any further. Okay, and in fact the liquid will maybe it will be slightly curved upward as well, but this will not rise any further, and capillary rise will stop if the height is less than the actual capillary rise height. Okay, so based on that we have seen some question came in the past in NEET exam, and this is simple easy question, that is why this might come in your KCET exam as well. So be prepared for this very interesting question. Okay, if you cut the pipe lesser height than the capillary rise, we will not see any infinite fountain effect. We will see that the liquid will stop at the maximum position of the pipe. Right? Clear? Now this is the end of this lecture, and if you have any doubts, don't forget to leave that in the comment below. Also, if you have not yet subscribed to our channel, don't forget to subscribe and give it a like to this video. I'll be back with more PUIQs and one more part of the second PU. First PU chapter is still pending. We'll come back with that. Till then, bye.